now that we know a little bit about gas laws, which we found through experiment, we need to take a look at kinetic molecular theory, which is the theory that underlies why we see the behaviors of gases that we do. So, quick reminder, or general principles if you've never seen this idea before, of why do we need a theory anyway? Well, one thing to think of is that you observe real-world phenomena out there. So, for example, in our setup here, things like P1 V1 equals P2 V2, right? Boyle's law is a real-world phenomenon. Or PV equals nRT. The ideal gas law is another ideal phenomenon. Pressure, volume, moles, and temperature are related to each other. And when scientists see a whole set of related phenomena, what we want to do is we want to say why. And so a theory's job is to explain where those phenomena come from. So underlying, what are the things doing that give rise to these observations that we make? And then last, what we do is we say, well, if the theory is right, I have some expectations about what might happen. And we formalize those into what we call a hypothesis, right? A hypothesis is essentially, if this theory is true, then this thing will happen. And so we make up a test and we see if we're right or not. And if we're not right, then we observe a different phenomenon, right? We don't observe what we thought we saw, and we fix the theory. And then we test the theory again. We say, well, I have a new hypothesis. And we keep iteratively looping this until we have a theory that does a good job at explaining things. So the theory in this case is, again, kinetic molecular theory is a name. And what do we need to explain? Well, we need to explain that pressure and volume are inversely proportional, right? That P1 V1 equals P2 V2 thing. We need to explain why volume and temperature are indirectly proportional or directly proportional to one another. If one goes up, the other goes down. We need to explain why pressure and volume and moles and temperature are related in this very specific way. And then there's what's called Graham's law of effusion and diffusion, that light gases will move more quickly than heavy gases, no matter if the temperature is the same. And so there's this interesting relationship between how fast a gas moves and comparing those things. And all of those need to be explained by a good theory of gases. And that good theory is called kinetic molecular theory. There's 5 main principles to that, or what we call postulates. So the word is postulate. A postulate is just a statement that we can't directly prove, but other things are true if this is true. So we can't prove that a gas has particles that are in continuous motion. We can't really watch that in a useful way, but Boyle's law only makes sense if gas particles are moving in straight line continuous motion. And so what we mean by that is, if I have a container of gas and it's closed, this gas molecule is moving in a straight line until it hits something. That could be a wall, it could be another particle. And then when it hits something, it changes its direction and goes in another straight line. So straight line, continuous motion, and the only thing that changes the straight line is collisions, right? So collisions with other particles or with the container. The other thing that we think of is that in a gas, particles are super far apart. And so they're tiny compared to the distance between them. What that does for us in kinetic molecular theory is that lets us say that the volume of the gas is equal to the volume of the container. That turns out to be a big deal. And that's only because the particles are tiny and there's huge spaces between them. Another thing that kinetic molecular theory does is it says that pressure comes from all those gas particles hitting the walls of the container and exerting force. Fourth postulate is that gas particles don't interact with one another, which just means that when they collide with each other, they bounce straight off. The picture you want in your head is of billiard balls, so think about playing pool, right? The balls bounce right off of one another. They're not Velcro balls where they hit each other and they stick together. They bounce and keep going. And the name for that is an elastic collision. They transfer energy between one another, but no energy is lost. Lastly, this idea of average kinetic energy, so we'll use KE for that. being proportional to the temperature of the gas. So the hotter the gas, the faster the particles are moving. Those are the principles of kinetic molecular theory. And it turns out that those 5 together can help us recover Boyle's law, Charles' law, ideal gas law, Graham's law of diffusion, and effusion. And so that's an important thing to know. So let's take a look at this idea of average kinetic energy, because that's probably the least familiar of all of them. What I want you to know is that when I have a container of gas particles, they all have slightly different speeds. And so I'm going to use the letter U to describe speed. And it's actually a distribution. So this thing here is called the distribution. And it's actually got 2 guys' names attached to it. It's called a Maxwell-Boltzmann. Lots of things in chemistry named after dead guys. And these 2 were named Maxwell and Boltzmann. So not all the particles are traveling at the same speed, which could be a problem if we did calculations later. Because imagine if I needed an average speed. Well, if I have a mole of particles, you guys know how to do an average. You'd add up all the speeds and you'd divide by all the particles. But if I'm adding 6.02 times 10 to the 23rd speeds, I'm going to be here all day. So what we do instead is we take advantage of the shape of this curve, and we describe 2 things. The first one up here, mu p, is called the most probable speed. Why is it the most probable speed? Because if you notice the y-axis, it's the number of molecules. And this speed has the most number of molecules traveling at it. Turns out not to be the one we're super interested in, though. The one that we really like is called URMS. It's called the root mean square speed. And URMS turns out to be better at describing how a bunch of gas particles behave than UP. So if I'm going to do calculations, I'm going to use something like URMS, or an average speed as well, as another way I might do it. But this root mean square speed, do you notice that it's related to the square root of 3 times the ideal gas constant? And by the way, there's another version of the ideal gas constant. This one is 8.314 joules. Oops, 8.314 joules per Kelvin. This T is the temperature in Kelvin. And then this M is the molar mass. And it would have to be in kilograms. We don't actually use this. What we do instead is we compare 2 speeds. So we'd say URMS of gas 1 divided by URMS of gas 2. And by the way, what that would end up being is the square root of 3RT over molar mass, and then fractions, right? It'd be the square root of molar mass 2 over 3RT. And so we don't see this. What we end up seeing is that it's the square root of M2 over M1. This right here is what we call Graham's law, which you read about in your book, Graham's law of diffusion. If you want to compare the speeds of 2 molecules, all you have to do is compare their molar masses. And we had said before, light molecules travel faster and heavy molecules travel slower. That's all in here, right? If I put in a bigger molar mass, if M goes up, speed goes down. If things get lighter, U gets higher. Why? Because they're inversely proportional. One of them is in the numerator and one of them's in the denominator. The other thing I want you to know is that there's a relationship between temperature and speed. And you notice that these are all speed distributions. And what do you notice as temperature goes up? I see a flatter distribution. So I see a wider, right? Wider is probably a better word for this. A wider distribution. And I also see that URMS goes up, just as I would expect. And so just be aware that there's this relationship in temperature. Higher temperatures mean a wider distribution of speeds, but always a higher average speed. Again, relating this to molecular weight, right? Xenon is the heaviest and helium is the lightest. What did we say? Lighter molecules, or lighter particles, I should say, because these aren't molecules, these are all atoms. Lighter particles have a wider distribution of speeds and a higher root mean square speed. So they're on average traveling faster. In another video, we'll take a look at real versus ideal gases.